Hi everyone, welcome back to another physics webinar. Today's webinar is going to be on velocity and acceleration. As always, the webinar is 1 hour long and will be recorded and uploaded onto YouTube so that you can refresh, revise and get down any notes that you may not have been able to get down during the webinar. If you don't know me already, my name is Preshayla. I study physics at Loughborough University and it's my 4th year as a tutor. So what we're going to be covering today is what is the difference between speed and velocity? Why do we have two different names for the same thing? Velocity in a circle, so what is special about circular motion? The speed distance time relationship, which you're probably already familiar with, but going into a bit more depth. Distance time graphs, velocity time graphs, and a new equation called the constant acceleration equation. Then there'll be a small quiz and we'll go through some exam questions and your questions. Okay, so first of all, let's think about what we looked at last week, which is this idea of suspended equilibrium. So suspended equilibrium is when we have something that is hanging. It might be from a cable, some ropes, some string. It might even be your light switch. So if you have one of those dangling light switches, that's in suspended equilibrium. So what it is when we suspend something, it tends to come to this rest point. Okay, so it's just dangling there, nothing's touching it, no wind's blowing on it, it's just resting. And when it's at this rest point, when it's at this equilibrium, the point at which it hangs from is directly above the object's center of mass. So what we mean by that is, let's say we've got a basket hanging from a kind of frame. So this is our basket here, hanging from our frame. Okay, this is our frame. So our basket is hanging, and what I've just said is that the point at which it's hanging from, so this point right here in blue, is the point at which it's hanging from. And suspended equilibrium says that the object's center of mass lies directly beneath that. So we can see that the object's center of mass in pink lies directly below the point at which it hangs. Seems obvious because we see it so often in day-to-day life, but it's just giving it a more formal definition, which is suspended equilibrium. Then we went on to talk a little bit more about the center of mass and how to find it. So we looked at regular shapes and irregular shapes. Regular shapes are, your standard circle shape, square shape, triangle shape. As we know, in real day-to-day life, there are hardly any objects which have a perfect circular, rectangular, triangular shape. And so to find the center of mass of an irregular shape, we looked at a special method. So that method was taking our irregular shape, however irregular it might be. So let's say we have this one, and we're going to put some holes in the corners. So I'll put one hole there, probably put one hole there and one hole there. So I've got 4 holes. And then what I do is I hang it from a clamp stand. So we've all seen our clamp stands in the labs, and you're going to hang your piece of paper that you're trying to find the center of mass of from these holes each in turn. What you're also going to have on your clamp stand is a plumb line. Now, a plumb line is basically a piece of string with a little, what we call a bob on the end, which is just a weight. It might be 100 grams, might be 200 grams, doesn't matter, but it's basically suspended from the string. And then we go on to put our card onto our stand as well. And what we'll find is that the card will hang by this hole and the plumb line will dangle straight down. And what we want to do is trace the line of the plumb line onto the card. So what we'll get effectively is a line that goes down like this. And then we do the same for each of the holes. So now we'll do it for this hole, and what we'll find is our line will go something like this. and then we'll do it for this hole, and then we'll do it for this hole. And what we'll find is that these lines that we've drawn come to a single point of intersection. That point of intersection is the center of mass, okay? Then we moved on to looking at gears, so changing gears, what it means to be in a low gear, in a high gear, changing gears, and how the shafts rotate, which creates a moment. Then we looked at moments, which is force times the perpendicular distance from the pivot, and just being really specific with what distance we are taking. So it needs to be the perpendicular distance from the pivot and not just any distance. We also looked at the principle of moments, which says that the sum of the clockwise moments about a point equals the sum of the anti-clockwise moments about that same point. So it's not left and right moments, it's clockwise and anti-clockwise moments. Finally, we looked at parallelogram of forces, which is if we have an object, let's say we have a boat and it might be being towed, and you've got two tensional forces in the string, we can create a parallelogram of forces from that and find the resultant force. So that was all to do with scale diagrams, and it's quite a complicated topic and therefore doesn't come up in the GCSE that much, but it is important to know. And if you did miss parallelogram of forces, then I would highly recommend you go back to the webinar and have a look because it's quite important. Okay, so let's move on to today's topic. Now, most of you will have heard of displacement and distance if you're in year 11 or year 10. But what is actually the difference between displacement and distance? They pretty much mean the same thing. They're both measures of distance, but distance we call a scalar quantity. And a scalar quantity means that it doesn't have direction. So we don't know what direction this distance happened in. It could have been east, it could have been north, it could have been on a bearing of 45 degrees. We don't know. And so distance only tells us a limited amount of information. All it tells us is how far an object moves. Displacement is distance's kind of pair, but displacement tells us the direction that the distance happened in. For this reason, it's called a vector quantity. It not only tells us how far an object moves, but also in which direction the object moves. So distance is a scalar, and a scalar has magnitude, which basically means the value of the distance. So 6 kilometers, 3 meters, whatever, it's the size. So the size of the quantity, and then you also have direction. So scalars only tell you the magnitude, displacement tells you the magnitude and the direction. So a little example that I'll use is this example here, which takes your house. So let's say your house is on the left and your school is on the right, okay? And it might be 2 miles to your school, just as an estimate. Now to work out the distance, there and back, all we need to do is do 2 miles plus 2 miles. And that tells us the distance. We don't really care about the direction, because distance doesn't tell us direction. It only tells us how far we've actually moved. And so the total distance that you've moved going from your house to school and school back home is 4 miles. Displacement, however, tells us the direction. So to go from your house to school is 2 miles east. But to go from your house, from your school to house is 2 miles west. Now, what's really special about this is that because you've gone 2 miles east and then you've come back 2 miles west, your displacement is actually 0, okay? Now, the reason for this is because they cancel out. They're in opposite directions, and therefore they cancel out. So yes, we have elapsed 4 miles as a distance, but because displacement has direction, those directions cancel out and we actually get a displacement of 0. So actually, theoretically, you haven't moved from your house. Okay, so we have the same kind of thing with speed and velocity. So speed and velocity are, again, counterparts. They're kind of a pair, they come together. They pretty much mean the same thing. Speed means, speed is a scalar quantity, so it does not have direction. Velocity is a vector quantity. So scalar has magnitude and just magnitude. Velocity has magnitude and direction. So speed is the scalar, velocity is the vector version. Okay, so what you need to know for speed is you need to actually know these common speeds and you need to be able to talk about them in relation to each other. So let's take our first one, walking. Walking is at an average of 1.5 meters per second. That's not to say everyone walks at 1.5 meters per second. It's just the average. Running is an average of double walking, so 3 meters per second. Cycling is double that again, so 6 meters per second. So we've come from walking at 1.5 to running at 3 to cycling at 6. And then sound, you also need to know the speed for, which is 330 meters per second. And so you can compare these to each other. You can say that cycling is 4 times that of walking. Sound is 100 times that of running, and so on and so forth. And so a GCSE question might ask you, how do these speeds relate to each other? Or you might have calculated a speed for something. So let's say a marathon runner, for example. And then the question asks you, compare this to the average running speed. And the marathon runner might be quicker than the average running speed. Okay, so we need to know these common speeds in order to be able to compare other speeds to them. Okay, so let's look at some examples of other scalars and other vectors. So in the top here, you can see some other scalars. Remember, scalars, only magnitude, no direction. So some other examples of scalars are energy. We never know what direction energy travels in. Power, again, power is got absolutely no relevance with direction. We don't care what direction the power moves in. And time, well, time doesn't have a direction. So these are some more examples of some scalars. And in a GCSE question, you might need to list off maybe 3 or 4 scalars. So you could say speed, you could say distance, energy, power, time, any of those. Vectors then, some other examples are acceleration and momentum. So acceleration always has a direction. You might be accelerating downwards, forwards, backwards, and even upwards. And momentum also has a direction. Okay, so velocity we know is this idea of speed with direction. Now in the higher tier of AQA and indeed other examples, you need to know about circular motion. So we have loads of examples in day-to-day life of objects moving in circular motion. Circular motion just means motion in a circle. Okay, so what are some examples of circular motion that we see in day-to-day life? Well, we have cars on roundabouts. Okay, so let's take that. for an example. So our car is moving around our roundabout in circular motion. And we say that at any given moment, the velocity acts at a tangent to the circle. Okay, you may not have heard this word tangent before, but what tangent means is it kind of flies off of the circle. So it's this line which only touches the circle at a single point. So this would be a tangent, this would be a tangent, this would be a tangent, and this would be a tangent. So we can see that it's these lines that just touch the circle at a single point. Okay, that's what a tangent is. Those blue lines are called tangents. So we say that at any given point, let's say here, the car's velocity is in a direction that is at a tangent to the circle. I'm going to write that down because it's quite a lengthy description. At any given point or time, the velocity of the object, could be a car, could be something else, is in the direction of the tangent to the circle at that point. So we can see that when the car is at this blue dot, the velocity v1 is in the direction of the tangent to the circle at that point. And the same over here at this blue dot. When the car reaches this blue dot, the velocity of the car is in the direction of the tangent to the circle at that point. Now this is weird because if the velocity is going to act in kind of a way that flies off of the circle, why does our car not just continue into that direction? Right? That's kind of weird because if the velocity is just going to fly off, why is our car not flying off the roundabout? Why is our velocity not going in that direction? Well, the reason for this is that the velocity is constantly changing, right? Because we have a certain velocity here, v1, but literally a second after, that velocity changes direction. Okay, so when the car reaches here, that velocity is now in a completely different direction. And when the car reaches here, again, it is a completely different direction. And this means that the velocity is constantly changing. Okay, absolutely constantly changing. Now, if the velocity is constantly changing, this means that we have acceleration. Again, really weird. So we know that our velocity is constantly changing. And if we have a change of velocity, this means it's accelerating. But your car is still going at the same speed, still doing 10 miles per hour or whatever it is, but it's accelerating. Really weird because we've always thought about acceleration to be getting faster, right? When you accelerate in a car, you get faster. That's what we've always thought about it as. But actually, acceleration is a change in velocity. The change in velocity does not necessarily mean the change in speed. Okay, change in velocity could just mean changing direction. It doesn't need to mean changing speed. So let's write that down. Changing velocity could be changing speed or changing direction or both. So for the example of circular motion, although we don't change speed, we constantly change direction. And therefore we could say that it's accelerating. So changing velocity doesn't necessarily need to mean changing speed, doesn't need to mean getting faster. It can just be changing direction. And therefore, when an object moves in a circle, we say that it accelerates. Weird. Okay, so we've got to kind of break apart from that definition that we used to have of acceleration, which is getting faster, and look a bit deeper into it and say that actually acceleration doesn't necessarily mean getting faster, it can just mean changing direction. Okay, let's look at our basics speed, distance, time equation. I think it's probably the first equation that you learn in physics, and one of the most common in the GCSE. Now, this is the speed, distance, time equation, but probably like you've not seen it before. What you're probably thinking is that S is speed, V, well, we don't really know V, so let's just call it velocity, and T, okay, we'll call that time. But now we've hit a problem because we've got speed and velocity in the same equation, which doesn't work. So this is a really weird point in physics. What you're used to seeing is speed equals distance over time with all the correct letters that show the beginning letter of the word. So speed equals distance over time. That all works. But now what they've done is they've changed the letters round and made us pretty confused. The reason that they've had to change them is to account for vector quantities. So this pink version of the equation is the scalar version of the speed, distance, time equation. But the green equation is the vector version of the equation. And it's very easy to get confused because they use pretty similar letters. Now, from the scalar to the vector equation, we can see a few differences. However, the similarities that we can see are time. T is time, always. Doesn't matter what equation we're using, time never changes. And that's because time is a scalar, and therefore it doesn't have a vector counterpart, doesn't have a vector pair. Time just doesn't have direction, it never will. So T is T in both versions of the equation. D, we don't have in our vector equation. And that is because D turns into S. And bear with me, it does get complicated. So D turns into S. And that is saying that distance goes to displacement. So S is no longer speed. S is displacement. Now this speed goes to velocity. So now we have our new vector equation. Displacement equals velocity times time. So we can see that we have two different forms of the same equation, one in scalar version, one in vector. Now let's take our vector version and put it into a triangle. You can see that we have S at the top, V and T at the bottom. So to use our triangle, we know that whatever we need to find, we have to cover up. So let's say we want to find S. So we cover S up and we see that we've got V and T left. Because V and T are next to each other, we need to multiply them together. Let's now say that we want to find V. So we cover V up, whatever's left is S and T. And because they're on top of each other, we do S divided by T. So this is our speed, distance, time equation. Okay, let's look at the distance-time relationship. So the distance-time relationship is something that is often plotted on graphs so that we can see how the distance changed with time. So on the y-axis, we have distance, and on the x-axis, we have time. Notice that on the y-axis, we have kilometers, and on the x-axis, we have time in hours, really. So it's going from 9 o'clock to 10 o'clock to 11 o'clock. If an object moves in a straight line, we can show it on one of these graphs. So from 9 to 11 o'clock, what this graph shows is that from 9 to 11 o'clock, the person has moved 30 kilometers. Then from 11 to 12 o'clock, the person hasn't moved at all. The distance doesn't go up. Then at 12 o'clock, they start again. And from 12 o'clock to 12:30, they move 30 kilometers. And from 12:30 to 2 o'clock, they move 60 kilometers. Okay. Now, we can find out some helpful things from this distance time graph. The first helpful thing that we can find out is the velocity. The velocity on a distance time graph is represented by the gradient. How do I know this? Well, the gradient of the line is how far up it is divided by how far across it is. So it's the change in the y value divided by the change in the x value. So we can see that the change in the y value is 30 kilometers. And the change in the x value is 2 hours. To find the gradient, we need to divide them by each other. So the change in the y value, or distance in this case, divided by the change in the x value, or time. And so we have the change in the distance, which is 30 kilometers, divided by the change in the time, which is 2 hours. And so we have 30 divided by 2, which is 15. And we divide the units as well to get 15 kilometers per hour. And that's how you find the velocity from a distance time graph. Now, for the next part of the graph, this flat section in pink, you can see that there is no change in y. From here to here, there is no change in distance. Therefore, a straight flat line means that they're at rest, they're not moving. If we have a flat line on a distance time graph, although time is still going forwards, they're not moving anywhere. And therefore, the velocity is 0. It has a 0 gradient. Then we have the next section of the line, which is this purple bit here. And again, we can find the gradient of the line. So it's the change in the y divided by the change in the x. Here, the change in the y is 30 kilometers. And the change in the x is 12 to 12:30, so 30 minutes. So when we do 30 kilometers divided by 30 minutes, we do, first of all, we deal with the numbers. So we do 30 divided by 30, which is obviously 1. Then we deal with the units. So we do kilometers divided by minutes, which is kilometers per minute. So 2 things that we need to remember with distance time graphs, the most important things. Number 1, check the axis. With distance time graphs, they sometimes mix up the units that we're used to working with. We are used to working with meters and seconds, but sometimes they switch it up. They might do kilometers, they might do miles, they might do hours, they might do minutes, they might do seconds, and they might do any combination of any of those 2. So we need to be wary of what units we're working with. Once we've checked the units that we're working with, we divide the units by each other, first of all, and then we divide the values. Sorry, we divide the values by each other, and then we divide the units by each other. So it's not like our normal divisions where we just do the numbers divided by each other and the units sort themselves out. It's more to do with dealing with the numbers first and then dealing with the units. Okay, so not just a simple division anymore. We're doing 2 divisions really. We're dividing the values and we're dividing the units. Okay, so finally, our last part of our graph is this blue graph. This blue part here. Again, we can do the change in y divided by the change in x. You see the change in y for the blue part is 60. And the change in x is 2.5 hours, so 2.5 hours. No, 1.5 hours, sorry. Okay, so the change in the y is 60 kilometers and the change in the x is 1.5 hours. So again, we divide our values. We do 60 divided by 1.5 and kilometers divided by hours. So can you put your answers in the chat? What do you think the velocity might be? If we're doing distance divided by time or displacement divided by time, what is the velocity? What do we think? Put your answers in the chat. Okay, so someone has said 40. Now, 40 is correct for the number because we do 60 divided by 1.5. And then we need to do our second division, which is the division of the units. So we do kilometers divided by hours. So our units are kilometers per hour. Okay. So the summary of this is that from a distance time graph, we can find the velocity by finding the gradient of the line, where the gradient of the line is the change in the x divided by the change in the y divided by the change in the x. So here shows you again what each feature of the graph looks like. So for a straight flat line here, it's at rest. A straight slanted line is constant speed, which we can find out by finding the gradient. And then a curved line shows us changing speed or acceleration. And we're going to work out acceleration from a distance time graph in the next webinar, because it's a bit more of an advanced topic and it's a higher topic to find the gradient of a curved line. So that was just another example. If you want to have a look later, this is what I'm going to be doing next time. Okay, so let's talk about acceleration. Acceleration is the change in speed divided by time. Pretty simple equation, and again, you can put it into your triangle if you want, where your top of your triangle will be velocity, delta v, and the bottom two will be a and t, if you want to put it into your triangle. Okay, so notice that we now have the change in speed. Not just speed, the change in speed. And notice that also, instead of s for speed, we have v for velocity, because we're taking into account the fact that we might have to deal with vectors. The third thing that you'll notice, which you might not have seen before, is this weird looking triangle. The triangle is called delta in Greek. It's a Greek letter, and it stands for the change in. So by putting a triangle in front of v, I'm saying the change in velocity. It's just a nice little way, instead of saying change in v, we represent it using this triangle. Then we divide by time, and we have our final equation, a equals delta v over t. Now delta v is this equation here. To have a change in speed, you need to have two different speeds which you can subtract from each other. So the change in speed is the final speed minus the initial speed. Could be 0 and 5, it could be 6 and 12. You need to have two speeds to be able to find the change in speed, right? So the change in speed, delta v, has its own little mini equation, which is final speed minus initial speed. So you might need to do a bit of maths before you put it into the acceleration equation. The third thing that we need to talk about is the units. The units can get pretty complicated with acceleration. We'll have a velocity in meters per second, and we'll have a time in seconds, which therefore makes our acceleration meters per second squared. So the units for acceleration are meters per second squared. So this brings us on to our velocity time graph. Our velocity time graph is completely different to a distance time graph. This time, our gradient shows us acceleration. In a distance time graph, gradient is velocity. In a velocity time graph, gradient is acceleration, because we have the change in v divided by the change in t, which is exactly what our equation is. Change in v divided by the change in t. So we can see that the gradient of a velocity time graph is acceleration. Gradient is acceleration. A straight flat line now means constant speed. Before, a straight slanted line meant constant speed, but now in a velocity time graph, a straight flat line means constant speed. Thirdly, we have another important piece of information that we can extract from a velocity time graph. That other important piece of information is this. The area under the graph shows us the distance, or the displacement. So to find the area under the graph of this graph, you might want to split it into three shapes, because finding the area of this red shape is pretty difficult. So you might want to split it into three different shapes. This triangle on the left, this rectangle in the center, and this triangle on the right, and then find the area of each of those parts. Remembering that the area of a triangle is the base times the height divided by 2. Area of a rectangle is simply the base times the height, and the area of the triangle again is base times height divided by 2. So once you've added up all of that area under the graph, we have our distance. So in a speed or velocity time graph, we get two important bits of information. The first one is that the gradient is the acceleration and the area under the graph is the distance or the displacement. In a distance time graph, we only get one important piece of information, and that is that the gradient is the velocity. So another important thing to remember when we're dealing with distance time graphs and velocity time graphs is to actually check the axis. Do you have a distance time graph or do you have a velocity time graph? Because the gradients are going to mean two very different things. Okay, finally then we have the constant acceleration equation. And this is a new equation and it's a pretty nasty equation. You can't put it into a triangle and it's got quite a lot of different terms to deal with. And what it does is it takes everything that we've learned today and puts it into one big equation. So the bit in red you can see is V. V stands for final velocity. The bit in blue is initial velocity. U means initial velocity. The bit in green is just a factor of 2. The bit in orange is acceleration, which we have as our A. And the bit in green is distance, represented by an S. So be careful. The S means displacement. This S is not speed, it means displacement or distance. Okay, so the final equation then is V squared, final velocity squared, minus initial velocity squared, U squared, equals 2 times A times S. If you have an object that is falling on this planet, then that acceleration is automatically 9.8. If it's falling, free falling through the air, the acceleration is 9.8. That's only if it's free falling through the air. So that's one thing to be careful of. Okay, so let's try some questions. And you can see here that a biscuit is dropped 300 meters from rest from the Eiffel Tower. Calculate its final velocity. So we've got our Eiffel Tower here. And let's say that this person is stood right here. Okay, they're looking out of the, I don't know, like the balcony of the Eiffel Tower. This distance is 300 meters up. So this person is at a height of 300 meters on the Eiffel Tower. So we have S, displacement, which is 300 meters. We want to find its final velocity. So we need to use our equation V squared minus U squared equals 2AS. To find final velocity, V, we need to rearrange our equation to get V, the subject. So the first thing that I'm going to do is move U squared to the other side. To move U squared to the other side, because it's already subtracted, I need to add it. So I do 2AS plus U squared. Then I can square root. Because I have my V squared, I need to square root both sides to get rid of a square. Remember, square root is the opposite of squaring. So to get rid of the square root, I square root. To get rid of the squared, I square root V squared, so I get V. And that means I have to square root the other side because I square root to the left-hand side. So I then get a really, really nasty equation of 2AS plus U squared. Now I can fill in all of my information. So to find V, final velocity, I need to do the square root of 2 times a. Now, what is a? Well, it's acceleration due to gravity, 9.8, because we have the object free falling through air, times s. S is displacement, which we know is 300 meters, plus u squared. Now, u is the initial velocity, but because the biscuit is dropped from rest, the initial velocity is just 0. So it's just plus 0 squared, which is obviously the same as doing absolutely nothing. So we'll just get rid of that. So now we have v is the square root of 2 times 9.8 times 300. So let's do that. Let's do 2 times 9.8 times 300 on our calculators, and we will get an answer of 5,880, which when we square root, we get 77 meters per second. So our final answer for the final velocity is 77 meters per second. These are one of the hardest questions in the GCSE. So please don't worry if you've not understood completely this time. We're going to be doing lots and lots of example questions around this equation. The worst thing about this equation is just how big it is and how many terms we need to account for. The rearranging can sometimes be difficult, and that's something that we can practice. For now, I think we'll have a quick quiz to finish off what is some quite heavy content. Quiz is only 9 questions long and they're all multiple choice. They're quick fire questions, so it shouldn't require too much working out. There is 2 maths questions in there which you'll need to use equations for. If you've not done the quiz already, then what you need to do is enter joinmyquiz.com into your browser. So up here in this bar here, on your desktop, on your laptop, on your computer, on your smartphone, on your iPad, it works on anything. You don't need to be on the Zoom. You don't need to be on Zoom, you don't need to be seeing my screen, it will all come up on your screen, so you can switch off and open a new tab, type in join my quiz, press join a game, and then you'll be able to type in the code. Yeah, so enter a game code, and the game code for today is 825742. 825742. If you can't put the game code in for whatever reason, I'm going to put the link on the Zoom chat so you can access it from there. So if you want, you can do it on the Zoom chat through the link. Okay, let's wait a few more seconds. Okay, we'll start the quiz. Good luck. And don't worry if you get a few questions wrong, because we'll be going through it at the end anyway. Have your calculators on hand, because you may need to do some maths. Okay, let's go through the answers. So for the first one, quite a few of you got it correct. A typical walking speed is 1.5 meters per second. This question is a bit tricky because it's worded a bit differently. It says, what quantity is the rate of change of velocity? The rate of change of velocity is acceleration. The rate means divided by time. So you can see here that the rate of change of velocity is acceleration. Acceleration is velocity divided by time. So another way of defining acceleration is the rate of change of velocity. How is speed found from a distance time graph? It's the gradient of the line. What is the acceleration of a horse that accelerates from rest to 4 meters per second in 8 seconds? Well, the change in velocity is 4 because it goes from 0 to 4. So the change in velocity is 4 and the time is 8. Acceleration is the change in velocity divided by the time. So the change in velocity is 4 divided by the time, which is 8. So we get 0.5 meters per second squared. What is the unit of acceleration? Meters per second squared. What is a typical speed for a bike? 6 meters per second. How is velocity found from a velocity time graph? It's read from the y-axis. What is the average speed of a runner that travels 200 meters in 40 seconds? Well, that's just distance over time. So 200 divided by 40, which is 5. How is displacement found from a velocity time graph? That is the area under the graph. Okay, so one thing that I will say about this topic is it takes some getting used to. And that is because what we've seen, the distance time graph and the velocity time graph, look really similar. We have flat lines and we have slanted lines with the area under the graph. We have the gradient, and it's so many different features of the graph that we need to consider. And they all mean different things between the distance time graph and the velocity time graph. So what I'd say to you is you just basically need to memorize what each of the features of those graphs look like. Okay, so the features of the distance time graph: what does the gradient mean? What does a flat line mean? What does a curved line mean? And then on a velocity time graph, what does the gradient mean? What does a flat line mean? And what does the distance under the graph mean? Sorry, the area under the graph mean? Okay, so it's really just a case of defining what those features of the graph look like. Another thing to note is these speeds here. I know that you're not going to memorize them after an hour, and don't worry, no one's expecting you to, but the more that we can get used to working with these, the more that they're going to stick in your heads. And one tip for remembering them is that walking is half of running, and running is half of cycling, which makes sense because each is faster than the other. So as long as you know that walking is 1.5, you can double it up and double it up again for walking, running, and cycling. So unfortunately, there is quite a lot of memorization in this topic, and that can make it quite long. Sound is 330 meters per second. Again, just something that unfortunately we have to remember. Okay, let's just quickly do this one. So again, pretty similar to the biscuit example question. And that is v squared equals u squared equals 2as. So a new equation. And the reason that I know to use this equation is because I have two speeds and a distance. I don't have two speeds in a time, I have two speeds and a distance. The only equation I can use is this equation. So now we have to find acceleration. We have our final speed 24, v. We have our initial speed 0, rest. So I'm just going to pretend that u squared goes to 0. And so I'm just going to leave it like that, because there's a little imaginary plus 0 in there. Then I have 2 times a times s, where s is the distance 1.44. And I can change that into meters by timesing by 1,000, and I get 1,440. So what I've done there is just turned kilometers into meters by timesing by 1,000. Then I can divide both sides by 2 and divide by 1,440. So I've got rid of the 2 on the right hand side, and I've got rid of the 1,440 on the right hand side to be left with a. When I put this all into my calculator, I get a equals 0.2 meters per second squared. Don't worry if this equation is a bit tricky right now. It's got a lot of terms and we'll be working on it some more. That's the end of today's webinar. I hope you guys have learned lots. As always, it is uploaded onto YouTube later on today or this week, so you can go through the content, go through the questions again, so pause the video and have a go yourselves. And if you do want any kind of one-to-one style tutoring with a tutor like myself, then that is something that MyTutor offer, and you can go onto MyTutor, find a tutor, and find a tutor that suits your style and your needs. Okay, so I'll see you all next week. Thank you.